Somewhere in the distant darkness of the universe, there exists a black hole that should not exist. Not because black holes are rare, but because this one is far too large, far too early, and far too powerful for the universe we thought we understood. When astronomers first calculated its mass, they assumed a mistake. The numbers were checked again, and again, and again, but each time the same impossible answer returned. This black hole is so vast that if it replaced our sun, its boundary would stretch far beyond Pluto's orbit, swallowing the entire solar system many times over. And yet, we are not seeing it as it is today. We are seeing it as it was over 10 billion years ago, when the universe itself was still young, which raises a quiet, unsettling question. How did something so enormous form so quickly in a universe that had barely begun? Here on Velarin's Sleepy Space Mysteries, we've explored strange cosmic giants before. Like in our journey through the largest structures in the universe, but this one feels different. This one challenges the rules themselves. Tonight, we begin a slow journey across space and time toward one of the most mysterious objects ever discovered. And as we travel, we'll uncover not just what this black hole is, but what it reveals about the hidden history of the cosmos. If you enjoy calm explorations like this, consider subscribing, leaving a like, and turning on the bell so you don't miss future journeys. You can also support the channel through membership if you'd like. And before we begin, tell me, where in the world are you watching from tonight? To understand this black hole, we first have to leave everything familiar behind. Not just Earth, not just our solar system, but the entire galaxy that has ever felt like home. If you look up at the night sky, far away from city lights, you might notice a faint, milky band stretching across the darkness. That soft glow is our galaxy, the Milky Way, a vast spiral of stars, gas, and dust quietly rotating through space. Somewhere deep within it lies our sun, orbiting the galactic center once every 200 million years, carrying Earth along for the journey. And at that center, there is already a black hole. It is called Sagittarius A*, and it contains about 4 million times the mass of our sun. Even that number is difficult to truly grasp. It is large enough to anchor the motion of hundreds of billions of stars, large enough to shape the structure of an entire galaxy. But tonight's black hole is not 4 million solar masses. It is tens of billions. To reach it, we begin a quiet departure. Imagine drifting away from Earth, slowly at first, watching continents blur into oceans, and oceans into a single sphere of blue and white. The moon slips past, then the planets, each one briefly marking our path outward. Mars fades into a reddish point. Jupiter becomes a striped memory. The sun shrinks behind us, from a blinding presence into just another bright star. Soon, the solar system itself becomes indistinguishable from the countless others scattered across the galaxy. We continue outward. The nearby stars begin to thin, though not because they are disappearing, but because the distances between them are so immense that even light takes years to travel from one to the next. What once seemed like a crowded sky reveals itself as mostly empty space. After thousands of years of imagined travel, the structure of the Milky Way begins to emerge. From the outside, it is no longer a sky, but a shape, a vast spiral, its arms gently curving outward, threaded with glowing regions where new stars are being born, and dark lanes where dust obscures the light behind it. It is beautiful, but also humbling. Every star you have ever seen, every constellation, every story humanity has ever told about the sky exists within this single rotating structure. And now we are leaving it. As we drift farther away, two smaller companions come into view: the large and small Magellanic Clouds, satellite galaxies bound to the Milky Way by gravity. They appear like faint, detached fragments, quietly orbiting their much larger neighbor. Beyond them, another galaxy begins to grow. First, it is just a faint blur, but gradually it becomes unmistakable. This is Andromeda, a galaxy even larger than our own, containing perhaps 1 trillion stars, slowly moving toward us across the darkness. In about 4 billion years, it will collide with the Milky Way, merging into a new, larger galaxy in a slow cosmic dance that will unfold over millions of years. But we are not stopping there. We continue outward faster now, leaving behind not just one galaxy, but the entire local group, a small cluster of galaxies bound together by gravity. Dozens of galaxies drift past us, then hundreds, then thousands, each one a vast island of stars, each one potentially home to planets, oceans, atmospheres, perhaps even life. And yet, despite this unimaginable abundance, we have never detected a clear signal from another civilization. The universe feels full and empty at the same time. As we move farther still, something subtle begins to change. The galaxies are no longer evenly scattered. They begin to form patterns, filaments stretching across enormous distances, connecting clusters of galaxies like threads in a vast cosmic web. Between these filaments lie enormous voids, regions so empty that you could travel millions of light years without encountering a single galaxy. This is the large-scale structure of the universe. Not random, but shaped. Gravity has spent billions of years pulling matter into these patterns, guiding galaxies along invisible pathways formed by dark matter, a substance we cannot see, but whose presence is felt through its gravitational influence. We are now far beyond anything that feels familiar. The temperature of space here is just a few degrees above absolute zero, barely warmed by the faint afterglow of the Big Bang itself. It is quiet, almost perfectly still. And yet, as we continue deeper into this vastness, we are also traveling backward in time, because the farther we look, the older the light becomes. Every galaxy we pass is not just distant in space, but distant in history. We are seeing them as they were millions, even billions of years ago. The universe begins to look different. Galaxies appear younger, more chaotic, more active. Collisions are more frequent. Star formation is more intense. The calm, structured galaxies of the present give way to something more turbulent, more alive. And somewhere ahead, hidden among these ancient galaxies, there is a single point of light brighter than it should be. A beacon shining across 10 billion years of cosmic history. At first, it looks like just another star. But it is not a star. It is something far more powerful. And as we continue our journey, drawing closer to that distant glow, we begin to realize we are approaching the black hole. First, it does not look extraordinary. Just a single point of light suspended in the vast darkness, no larger than any other distant star in the sky. But something about it feels different. Even from this unimaginable distance, it shines with a quiet intensity that sets it apart. While nearby galaxies glow softly, spread across space like faint clouds, this object remains sharp, concentrated, almost unnaturally bright. As we continue drifting closer, that brightness does not fade or spread out as expected. It grows, and that is the first clue. Because in the universe, objects that appear small are usually either small or very far away. But when something remains intensely bright across billions of light years, it means only one thing. It is releasing an enormous amount of energy, more than entire galaxies. We move closer still, and now something strange begins to happen. The light from this object is not quite the color we expect. It appears shifted, stretched slightly toward the red end of the spectrum. Not dramatically to the eye, but enough that, if measured carefully, it reveals something profound. This light has been traveling for over 10 billion years. It has crossed expanding space itself, its wavelength stretched along the way, like ripples on a pond being slowly pulled apart. This effect, known as redshift, is one of the most powerful tools astronomers have. It tells us not just how far away something is, but how far back in time we are seeing it. And in this case, we are looking into an era when the universe was less than a quarter of its current age. A time when galaxies were still forming, when collisions were common, when everything was more chaotic, more energetic, more alive. And yet, even in that wild, young universe, this object stands out. We approach closer. Now, it begins to resolve slightly, not into a galaxy, not into a cluster, but into something far more compact. A brilliant core surrounded by a faint halo, like a lighthouse beam piercing through cosmic fog. This is a quasar. The word itself comes from quasi-stellar object, because when these objects were first discovered, they looked like stars. Small, sharp points of light with no visible structure, even through powerful telescopes. But their spectra told a different story. When astronomers split their light into its component colors, they found something impossible. The familiar fingerprints of elements like hydrogen were there, but shifted dramatically, far beyond what could be explained if these objects were nearby. They were not stars at all. They were billions of light years away, and yet they were visible. For that to be true, they had to be unimaginably bright, brighter than hundreds of billions of stars combined, brighter than entire galaxies. And still, somehow, confined to a region no larger than our solar system. It was a paradox. How could something so small produce so much energy? As we move closer, the answer begins to take shape. At the heart of this quasar lies a black hole. But not just any black hole. This one is feeding. Matter, gas, dust, entire streams of material is falling inward, spiraling toward the center. But it does not fall straight in. Instead, it forms a vast, rotating disk, known as an accretion disk, where everything slowly circles the black hole before crossing the final boundary. And as it spirals inward, it heats up. Friction between layers of gas, magnetic forces twisting and snapping, gravitational energy being converted into motion and then into heat. All of it builds, layer by layer, until the temperature rises to levels almost impossible to imagine. Millions of degrees. In some regions, even billions. At these temperatures, matter does not behave normally. Atoms are torn apart into plasma, electrons and nuclei moving freely, interacting through powerful electromagnetic forces. Light is emitted across the entire spectrum, from radio waves to visible light, to intense X-rays and gamma rays. This is what we are seeing. Not the black hole itself, which remains completely dark, but the glowing, furious storm of matter surrounding it. And the scale of this storm is beyond comprehension. The energy output of this single object is so vast that if it were placed even thousands of light years away, it would outshine every star in our sky combined. If it were placed as close as the nearest star, it would sterilize entire planets in moments. Oceans would boil. Atmospheres would be stripped away. Life would not stand a chance. And yet, from 10 billion light years away, it appears as just a point of light. This is the quiet deception of distance. But now, as we continue drawing nearer, the illusion begins to break. The point of light grows larger, brighter, more defined. The surrounding glow becomes more complex. Subtle structures begin to emerge, hints of motion, of rotation, of something vast and violent unfolding at the center. And with each moment, we come closer to understanding the true nature of this object. Because this is not just a quasar. This is one of the most extreme black holes ever discovered. A black hole so massive that even by the standards of the early universe, it should not exist. And yet, it does. As we move closer, the illusion of simplicity disappears. What once looked like a single point of light now begins to unfold into something far more complex. A structure shaped not by calm order, but by motion, gravity, and immense energy. The quasar is no longer just a distant glow. It is becoming a system. At first, the central brightness expands into a soft disk, slightly flattened, almost like a distant whirlpool seen from above. Around it, faint halos of light shimmer and shift, revealing that this is not a static object, but something constantly in motion. And then, slowly, the rotation becomes visible, not as a blur, but as a pattern. The outer regions of the disk move gently, almost lazily, like clouds drifting across a quiet sky. But as your gaze follows the structure inward, the motion accelerates. Layers of gas begin to overtake one another, forming spiraling currents that tighten as they approach the center. This is the first glimpse of the accretion disk in detail, a vast, rotating structure made of matter that is no longer free matter that has already fallen too close to escape, but has not yet crossed the final boundary. Here, gravity is no longer just a force. It is a guide, pulling everything inward while forcing it to orbit at incredible speeds. The closer the material gets, the faster it must move to remain in orbit. This creates a natural gradient across the disk. The outer regions may circle the black hole over years or decades, but the inner regions complete an orbit in days, or even hours. This difference in speed creates friction, not the kind we feel between solid surfaces, but a deeper, more complex interaction. Layers of gas slide past one another, transferring energy through turbulence, collisions, and magnetic forces. And this friction generates heat. At first, the temperatures are relatively modest by cosmic standards, a few thousand degrees. The outer disk glows with a dim, reddish light, similar to the surface of a cool star. But as we follow the spiral inward, the temperature rises steadily. Tens of thousands of degrees, then hundreds of thousands, then millions. The color shifts with it, from red to orange to white, and finally to a piercing blue-white glow that radiates far beyond the visible spectrum. By the time we reach the inner regions of the disk, the matter here is no longer recognizable as gas in any ordinary sense. It has become plasma. Atoms are stripped apart. Electrons and nuclei move independently, interacting through powerful electromagnetic fields that twist and stretch across the disk like invisible threads. These magnetic fields are not passive. They are dynamic, unstable, constantly changing. As charged particles move, they generate fields, and those fields influence the motion of other particles. The result is a feedback loop, a system that is both structured and chaotic at the same time. Occasionally, these magnetic field lines become tangled, stretched to the point where they suddenly snap and reconnect in new configurations. When this happens, energy is released. Suddenly, violently. These events, known as magnetic reconnection, create bursts of radiation, flares that ripple across the disk, briefly outshining even the already intense glow surrounding them. From a distance, these flares might appear as subtle flickers, but up close, they are immense. Explosions of energy that would dwarf anything seen in our own solar system. And yet, all of this activity, all of this chaos, serves a single purpose. It allows matter to fall inward, because without this turbulence, without this transfer of energy, the material in the disk would simply remain in orbit forever. It would circle the black hole endlessly, never crossing the threshold. Something must remove its orbital energy. Something must allow it to spiral closer. And that is exactly what this turbulent disk does. Slowly, gradually, layer by layer, matter loses energy and drifts inward, moving ever closer to the point of no return. As we watch this process unfold, another detail becomes clear. The disk is not uniform. It is filled with variations, denser regions, thinner regions, waves that ripple outward and inward at the same time. These patterns are shaped by gravity, pressure, and magnetic forces, all interacting in ways that are still not fully understood. It is not a smooth flow. It is a storm, a vast cosmic storm of billions of kilometers across, yet governed by the same fundamental principles that shape even the smallest interactions in nature. And at the center of it all, there is something we still cannot see: the black hole itself. It remains hidden, not because it is small, but because it emits no light. It is defined by the absence of light, by a boundary beyond which nothing can return. But we can feel its presence in the speed of the orbiting material, in the rising temperatures, in the way space itself seems to curve, subtly distorting the light around it. We are getting closer now, close enough that the structure of the inner disk begins to sharpen, close enough that the effects of extreme gravity will soon become impossible to ignore. And as we continue inward, we approach the region where physics itself begins to change, where time slows, where light bends, where reality no longer behaves the way we expect. Now, as we move deeper into this glowing storm, something subtle begins to change. At first, it is almost unnoticeable. The light from the disk, which once appeared evenly distributed, now seems slightly uneven. One side grows brighter, sharper, almost as if it is leaning toward us, while the opposite side fades, becoming dimmer, more distant. This is not an illusion. It is motion. The entire disk is rotating at extraordinary speeds. And now we are close enough to witness the consequences. The side rotating toward us appears brighter because its light is being compressed, shifted toward higher energies. The side moving away is stretched, dimmed, its light losing energy as it recedes. This is the Doppler effect, but taken to an extreme. Here, near the black hole, parts of the disk are moving at a significant fraction of the speed of light. Not thousands of kilometers per second, but tens of thousands, even approaching half the speed at which light itself travels. At these speeds, something even stranger happens. Light does not simply shift in color. It begins to concentrate. Radiation emitted by fast-moving matter is focused forward, beamed in the direction of motion. So the side of the disk rotating toward us becomes intensely bright, almost blinding, while the opposite side fades into relative darkness. This creates a dramatic imbalance, a disk that appears lopsided, even though in reality it is symmetrical. But the distortions do not stop there. As we move closer still, a gravity begins to reveal its deeper influence. Light itself begins to bend. Photons leaving the far side of the disk, which should have been hidden behind the black hole, are curved around it, redirected by the extreme warping of space. What should be invisible becomes visible, and so something extraordinary appears. A ring, a complete, glowing ring of light encircling a dark center. This is not a physical structure, not a ring of matter, but an optical effect created by gravity itself. Light from different parts of the disk is being bent, twisted, and redirected toward us, allowing us to see regions that would otherwise be blocked. We are seeing multiple sides of the disk at once, above, below, and even behind the black hole, all compressed into a single surreal image. At the center of this glowing ring, there is darkness. Not shadow, not absence of illumination, but a true absence, a region where no light escapes. This is the silhouette of the black hole, often called its shadow. It is larger than the event horizon itself, shaped not just by the boundary of no return, but by the paths that light can and cannot take through the curved spacetime surrounding it. For the first time, we are seeing the edge of something that has no surface. And as we continue inward, time itself begins to change. Not in a way we can feel directly, but in a way that reshapes everything we observe. Clocks closer to the black hole tick more slowly than those farther away. This effect, known as gravitational time dilation, becomes stronger the deeper we go. From our perspective, processes near the inner disk seem to stretch, to slow, even as they remain incredibly energetic. If we could compare two identical clocks, one far from the black hole, one near the inner edge, the one closer would fall behind. Time itself is being pulled, and space is not immune. Distances warp, paths curve, straight lines become arcs. Even the direction down begins to lose meaning, replaced by a geometry that guides everything inward. We are now approaching a critical boundary, a region known as the innermost stable orbit. This is the last place where matter can circle the black hole without immediately falling in. Inside this boundary, orbits are no longer stable. Any small disturbance, any slight shift, sends matter spiraling inward, unable to recover. Here, the motion is almost impossible to imagine. Material whips around the black hole in hours, perhaps even minutes. The energy released in this region is immense, far greater than in the outer disk. This is where much of the quasar's brilliance is born. And yet, this region is incredibly small compared to the full scale of the system. Most of the light, most of the energy, comes from a thin inner layer just before the final descent. It is here that matter reaches its peak. Maximum speed, maximum temperature, maximum luminosity, before everything changes. Because just beyond this region, there is no orbit, no escape, only inward motion. The event horizon lies ahead, invisible, silent, absolute. From a distance, it seemed almost abstract, a concept more than a place. But now, it is near, and as we drift closer, watching matter cross that unseen boundary, vanishing without a trace, we begin to understand something deeply unsettling. Nothing that enters ever returns. No signal, no light, no information, only silence. And yet, from our perspective, something strange happens. As matter approaches the horizon, it appears to slow, to fade, to freeze in time, never quite crossing. But this is only how it looks from the outside. In reality, the crossing happens, quietly, inevitably, and soon we will follow. We are now closer than anything we have ever imagined. The vast disk behind us stretches across space like a glowing ocean, but ahead, everything narrows, compresses, focuses toward a single boundary that cannot be seen, yet defines everything. The event horizon. It does not glow. It does not shimmer. It does not announce itself. And yet, it is the most important boundary in this entire system. From far away, it seemed almost theoretical, an idea defined by equations and predictions. But here, surrounded by the last light of the accretion disk, it becomes something else. Presence. A quiet, absolute edge where the rules change. We watch as streams of matter spiral inward, drawn closer and closer until they reach that invisible threshold. There is no flash, no explosion, no dramatic signal. The material simply disappears. One moment it is part of the universe we can observe. The next, it is gone, and nothing comes back. But something even stranger begins to happen as we observe more closely. Time itself appears to stretch. From our distant perspective, anything approaching the event horizon seems to slow down. Its motion becomes more gradual, more drawn out, as if the universe itself is hesitating at the edge. The light it emits becomes dimmer, redder, fading slowly into darkness. It never quite seems to cross. It just lingers, frozen at the boundary. But this is only what we see from the outside. If we could follow that falling matter, if we could drift alongside it, the experience would be very different. From that perspective, there is no pause, no hesitation, no visible barrier. The crossing happens smoothly, silently, in a single, continuous motion. One moment, escape is still possible. The next, it is not, and there is no turning back. This is one of the deepest paradoxes of black holes. Two observers witnessing the same event, but experiencing completely different realities. From the outside, time appears to slow and stop. From the inside, it flows forward, uninterrupted. Both are true, and neither can fully see the other. As we hover at this threshold, something else becomes clear. The scale. This black hole is not like the smaller ones often imagined. Its event horizon is not a tiny sphere, but an enormous boundary stretching across distances that rival our entire solar system. If placed where our sun is, its edge would extend far beyond Pluto, enveloping every planet, every asteroid, every distant comet. And yet, despite this enormous size, the transition across the horizon would feel almost gentle. For smaller black holes, the gravitational difference between your head and your feet at the horizon would be extreme, pulling you apart almost instantly. But for this ultramassive black hole, the curvature of space is more gradual at the boundary. You could cross it without even realizing, at least not immediately. The real danger lies deeper within, but that is still ahead. For now, we remain just outside, watching, listening, observing the final moments of matter before it vanishes from the visible universe. And in this quiet observation, another realization begins to emerge. Everything we are seeing, all this light, all this energy, all this motion, it is temporary. This black hole is feeding now, consuming vast amounts of matter, shining as one of the brightest objects in the universe. But it will not always be this way. The very radiation it produces, the very energy that makes it visible across billions of light years, is also pushing against the inflowing material. Light carries momentum. As it streams outward, it exerts pressure on the gas around it, slowing the flow, sometimes even driving it away. Over time, this feedback will begin to starve the black hole. The surrounding gas will heat up, disperse, escape. The brilliant quasar will fade. The disk will thin, dim, and eventually disappear. What remains will still be enormous, still powerful, still capable of shaping the galaxy around it. But it will no longer shine. It will become quiet, dormant, a dark center in a massive galaxy, surrounded by ancient stars, a relic of a more violent time. And this raises another question, one we have been quietly carrying since the beginning of this journey. If this black hole will one day fade, if it grew during a time when the universe was younger, more chaotic, more full of gas, then how did it grow so large, so quickly, in the first place? Because even now, as we stand at the edge of its immense gravity, the numbers do not quite make sense. There should not have been enough time, not enough fuel, not enough opportunity. And yet, here it is, a black hole so massive that it challenges everything we thought we understood about how the universe builds its largest structures. And as we prepare to move even deeper, beyond the boundary where light can no longer guide us, we begin to realize this is not just a journey into a black hole. It is a journey into a mystery that the universe has not yet fully explained. If you are still here, still drifting through this vast darkness with me, gently let me know by typing a quiet 1 in the comments. And when you're ready, we will continue deeper still. We are now standing at the edge of something that does not behave like anything else in the universe. Not a star, not a planet, not even a galaxy, but a region where gravity has become so dominant that it no longer simply pulls on objects. It reshapes the very structure of reality itself. And to understand what lies beyond this boundary, we must first understand what this black hole truly is. Because despite everything we have seen so far, the glowing disk, the immense energy, the violent motion, none of that is the black hole. All of it is only what surrounds it. The black hole itself is invisible. It does not emit light. It does not reflect light. It does not interact with light in any way that allows it to be seen directly. Instead, it is defined by a single idea: escape. More precisely, the complete absence of it. A black hole forms when enough mass is compressed into a small enough region that the speed required to escape its gravity becomes greater than the speed of light. And since nothing can travel faster than light, nothing inside that region can ever leave. This boundary, where escape becomes impossible, is what we call the event horizon. But here is where things begin to shift, because the event horizon is not a surface in the traditional sense. It is not made of matter. It has no texture, no resistance, no physical structure you could touch. It is a boundary defined purely by the geometry of space-time. A line drawn not in space, but in possibility. Outside it, the future still includes paths that lead outward. Inside it, every possible path leads inward. No matter what direction you move, no matter how fast you try to go, your future is already decided. You are moving toward the center. This is what makes black holes so different from everything else. They do not trap things by pulling harder. They trap things by removing all other options. And now, as we drift closer, we begin to see how this affects not just matter, but reality itself. The first thing to understand is that gravity here is not simply stronger. It is deeper. In everyday life, gravity feels like a force, something that pulls objects downward. But in the framework of modern physics, gravity is not really a force at all. It is the result of curved spacetime. Mass tells spacetime how to curve, and curved spacetime tells matter how to move. Near Earth, this curvature is gentle. Objects fall or orbit in predictable ways. But near a black hole, the curvature becomes extreme. Paths that once seemed straight bend. Directions that once felt independent merge. Even time begins to behave differently. We touched on this earlier, but here it becomes unavoidable. As we approach the black hole, time for us slows relative to the outside universe. Not because anything is wrong with our clocks, but because time itself is being stretched by gravity. If someone far away were watching us, they would see our movements slow down, our signals arrive less frequently, our entire existence appear to drift towards stillness. But from our own perspective, nothing feels different. Our thoughts flow normally. Our sense of time remains unchanged. This disconnect is one of the strangest aspects of black holes. Two observers, separated only by distance, experiencing completely different rates of time, and yet both are correct. Now, as we move even closer, another effect begins to emerge. Space itself begins to stretch, not uniformly, but unevenly. The closer part of any object feels a slightly stronger pull than the farther part. This difference is small at first, barely noticeable. But as we descend deeper into the gravitational well, it grows. This is what we call tidal forces. If you imagine falling feet first toward the black hole, your feet would feel a slightly stronger pull than your head. Over time, this difference would begin to stretch you, lengthening your body while compressing it from the sides. At first, the effect is subtle, but it does not stay that way. And yet, here is something surprising. Because this black hole is so massive, so enormous in scale, the curvature at the event horizon is actually quite gentle compared to smaller black holes. The tidal forces at this boundary are not immediately destructive. You could cross the horizon, and for a brief time, nothing dramatic would happen. No sudden tearing, no instant destruction, just a quiet continuation inward. This is one of the most unsettling truths. You could pass the point of no return without even realizing it. Only later, deeper inside, would the consequences begin to reveal themselves. But before we go there, we must pause at the boundary itself, because this is where two realities meet. From the outside, nothing ever seems to cross. From the inside, everything does. And somewhere between these perspectives lies a deeper question. What really happens to information when matter falls into a black hole? Its structure, its history, everything that defines it appears to vanish from the observable universe. But according to the laws of quantum physics, information cannot simply be destroyed. So where does it go? Is it preserved somehow at the horizon? Is it encoded in ways we do not yet understand? Or is something about our current understanding incomplete? This is not just a technical question. It is one of the deepest mysteries in all of physics. And this black hole, this enormous ancient object, may hold part of the answer. Because at scales like this, where gravity is extreme and time itself bends, we are no longer just observing the universe. We are testing its limits. And as we prepare to cross the boundary ourselves, we leave behind not just light, but certainty. We cross the boundary, and nothing happens. No flash, no shock, no sudden tearing of reality. Just a quiet continuation forward, as if we had passed through nothing at all. And in a sense, we have. Because the event horizon is not a wall, not a surface, not a place where something physically stops you. It is a threshold defined only by what is possible and what is no longer possible. Outside, there were paths that could lead away. Inside, every path leads deeper. And now we are inside. First, everything still looks familiar. The accretion disk behind us continues to glow, its light still reaching us, still painting the darkness with color and motion. But something about it feels compressed. The universe we came from seems to shrink, as if it is being pulled into a smaller and smaller region behind us. This is not just distance. It is geometry. Space-time itself is curving in such a way that all directions, even those that once pointed outward, are now subtly redirected inward. If we tried to turn around, if we tried to move away from the black hole, we would still find ourselves drifting deeper inside. There is no escape trajectory here, not because we are too slow, but because a way no longer exists. This is one of the most difficult ideas to truly grasp. Inside the event horizon, the direction toward the center is not just a place in space. It is the future. Just as you cannot stop moving forward in time, you cannot stop moving toward the singularity. It is not ahead of you in space. It is ahead of you in time. And this changes everything. We are no longer navigating space in the way we once did. We are not choosing directions. We are moving along a path that has already been defined by the structure of space-time itself. Still, for a while, the journey feels calm. The tidal forces we mentioned earlier begin to increase, but slowly. There is a gentle stretching sensation, almost imperceptible at first. Our feet feel a slightly stronger pull than our head. Our body begins to elongate, just a little, while being compressed from the sides. It is subtle, but it is growing. As we continue inward, the outside universe fades further. Light from distant stars becomes more concentrated, distorted into a shrinking patch behind us. The colors shift, becoming bluer, more energetic, as the light falls deeper into the gravitational well. Time outside appears to accelerate. Events that would take years seem to unfold in moments. The universe we left behind begins to race forward, its history compressed into a rapid sequence of change. Galaxies evolve, stars are born and die, all while we continue our descent, experiencing time at our own steady pace. This is the opposite of what an outside observer would see. To them, we would appear frozen at the horizon, fading slowly into darkness. But from here, it is the universe that appears to rush ahead. Two perspectives, two realities, both equally valid, and yet neither complete. As we move deeper still, the stretching becomes more pronounced. The difference in gravitational pull between different parts of our body increases. What was once a gentle elongation becomes a noticeable force. Our body is being pulled into a longer, thinner shape while being squeezed from the sides. This process has a name: spaghettification. It sounds almost playful, but the reality is anything but. For smaller black holes, this effect would begin before reaching the event horizon, tearing objects apart instantly. But here, in this ultramassive black hole, the process begins more gradually. The scale is so large that the curvature of spacetime changes more slowly near the horizon, giving us time to experience this descent. But that time is limited, because as we approach the central region, the forces increase rapidly. What was once subtle becomes intense. What was once survivable becomes overwhelming. Our body continues to stretch, longer, thinner, as the difference in gravitational pull grows stronger. The atoms that make up our body, once held together by electromagnetic forces, begin to feel the strain. At first, tissues separate, then cells, then molecules. Eventually, even atoms themselves cannot hold together. Everything that once formed a coherent structure is pulled apart, not violently, but inevitably. And yet, even as this happens, something deeper remains unresolved, because we are approaching a region that our current understanding of physics cannot fully describe. The singularity, according to general relativity. This is where all the mass of the black hole is concentrated into a point of infinite density, where space-time curvature becomes infinite, and the equations that describe reality break down. But infinities in physics are often a sign not of reality, but of the limits of our understanding. They tell us that something is missing, that our theories, as powerful as they are incomplete. And so the singularity remains not just a destination, but a mystery. What really happens there? Does matter truly collapse into an infinitely small point? Or is something else taking place? Something governed by laws we have not yet discovered? Some theories suggest that quantum effects may prevent true collapse, replacing the singularity with a region of extreme but finite density. Others suggest even stranger possibilities, that information is preserved in ways we cannot yet observe, or that the interior of a black hole may connect to other regions of space-time. For now, we do not know, and that uncertainty is part of what makes this journey so profound. Because as we fall deeper into this black hole, we are not just exploring an object. We are approaching the edge of human knowledge itself. As we continue falling inward, something profound begins to unfold, not just around us, but in the very meaning of space and time themselves. Up until now, we have imagined motion as something simple. You move forward, backward, left or right. You choose a direction, and you go. But here, those ideas begin to lose their meaning. Inside the black hole, directions no longer behave the way they once did. The deeper we fall, the more space itself bends in ways that make movement feel less like a choice and more like a consequence. Earlier, we said something strange, that the singularity is not just a place, but a moment. And now we begin to understand why. In the space outside the black hole, time is separate from direction. You can stand still in space while time moves forward. You can move in any direction while the future remains open. But inside the event horizon, this changes. The direction toward the singularity becomes unavoidable, like time itself. You cannot choose to stop moving toward it, just as you cannot choose to stop moving toward tomorrow. It is no longer a destination you approach. It is a moment you are moving toward. This idea is difficult to picture, because our intuition is built on a world where space and time feel separate. But here, they are intertwined in a way that reshapes everything. Imagine standing on a river. Outside the black hole, you can swim in any direction. You can move with the current, or against it, or sideways across it. But inside the black hole, the river becomes a waterfall. No matter how strong you are, no matter which direction you try to swim, the flow carries you downward. Not because you are weak, but because all possible paths lead that way. This is what space-time becomes inside the event horizon. A flow, not through space, but through reality itself. And as we are carried along this flow, something else becomes apparent. The structure of space-time is not smooth. It is dynamic, shaped by the rotation of the black hole itself. This black hole is not just massive. It is also spinning, and that rotation drags space-time along with it. This effect is known as frame dragging. It means that space itself is being twisted, pulled into motion around the black hole. Even if you tried to remain still relative to distant stars, you would find yourself slowly rotating, carried along by the fabric of space-time itself. Closer to the center, this effect becomes stronger. Paths that once seemed straight begin to spiral. Motion becomes more complex, more constrained, as if the geometry of reality is tightening around us. And then, something even more subtle begins to emerge. The difference between space and time begins to blur. Coordinates that once described positions begin to behave like moments, and moments begin to behave like directions. This is not something we can feel directly, but it is something that shapes everything around us. It means that the closer we get to the singularity, the less meaningful our usual descriptions become. Distance loses its clarity. Time loses its uniformity. And reality becomes something harder to describe. Still, we continue. The tidal forces increase further now. The stretching becomes more intense, more unavoidable. What was once a slow elongation is now a continuous pulling, a steady transformation of shape. But because this black hole is so large, the process still feels gradual compared to smaller ones. There is time to observe, to think, to wonder. And in that time, another question begins to surface. What does the singularity actually look like? We have described it as a point, a place of infinite density. But this description may not be accurate in a physical sense. It is a prediction of our equations, not something we have ever observed. In fact, it may not look like anything at all, because looking requires light, and near the singularity, light itself is trapped, unable to escape, unable to carry information outward. Even within this descent, what we can see is limited. We are surrounded not by clarity, but by uncertainty. And yet, there is a strange calm in this, a quiet realization that we are moving toward something fundamental, something that lies beyond our current understanding. Not chaos, but mystery. Not destruction, but transition. Because black holes are not just endpoints. They are questions. Questions about gravity, about time, about the nature of information, and whether it can ever truly be lost. And this black hole, this immense, ancient object, holds those questions within it. As we fall deeper, carried by the flow of space-time itself, we are not just approaching the center. We are approaching the boundary of what we know. And somewhere ahead, beyond the reach of our theories, the answer may be waiting, or perhaps something even stranger. As we descend further, deeper than any signal could ever return from, something begins to shift again. Not in a sudden way, not like crossing the event horizon, but gradually, almost imperceptibly. The environment becomes quieter, not because there is less happening, but because there is less we are able to perceive. Light, which once filled our view with swirling patterns and radiant energy, now fades into something dimmer, more fragmented. The glowing disk we left behind is no longer a wide, luminous structure. It has collapsed into a narrow, distant ring, shrinking further with every passing moment. The universe we came from is slipping away, and with it, our last visual connection to everything familiar. What remains is not darkness in the usual sense, but something more complete, a silence of information, because here, inside the black hole, light cannot freely move outward, cannot carry images, cannot reveal distant objects, cannot guide us in the way it once did. Our ability to see becomes limited not by blindness, but by the structure of space-time itself. And so we begin to rely on something else. Understanding. We cannot observe our surroundings in the traditional way. but we can still follow the logic of what must be happening. And what must be happening is that everything is being drawn inward faster, stronger, more intensely with every moment. The tidal forces, which were once gradual, now begin to accelerate. The stretching becomes more severe, the compression from the sides more intense. The difference in gravitational pull across even small distances grows rapidly. What was once a gentle gradient becomes a steep descent. If earlier it felt like being slowly pulled, now it feels like being continuously reshaped. The space around us is no longer behaving like a stable environment. It is dynamic, evolving, collapsing toward a center that we still cannot see, but cannot avoid. And yet, there is something deeply strange about this stage of the journey, because even as everything becomes more extreme, the experience remains smooth. There are no shocks, no turbulence, no sudden transitions, just a continuous, inevitable progression. This is one of the most counterintuitive aspects of black holes. From the outside, they appear violent, destructive, catastrophic. But from the inside, the journey can feel almost calm. Not because it is safe, but because the laws governing it are consistent, unbroken, quietly guiding everything forward. As we continue, another realization begins to form. The singularity, whatever it truly is no longer something far away. It is approaching rapidly. Remember, inside the event horizon, the singularity is not just a location in space. It is a moment in time, and we are moving toward it as surely as we are moving toward the next second. This means something profound. There is no way to delay it, no orbit to stabilize into, no path to take that avoids it. All possible futures converge there. And as we approach this final region, the limitations of our current understanding become impossible to ignore. According to general relativity, the equations predict that density becomes infinite, that curvature becomes infinite, that space-time itself collapses into a point of zero volume. But infinities in physics are warnings. They tell us that our model, our description of reality, has reached its limits. They tell us that something deeper is missing. And this is where quantum physics enters the story. On the smallest scales, the universe does not behave continuously. It is discrete, governed by probabilities, by uncertainties, by interactions that do not align cleanly with the smooth geometry of general relativity. Somewhere near the singularity, these two frameworks must meet: gravity and quantum mechanics. But we do not yet have a complete theory that unites them. We do not yet know what replaces the singularity when quantum effects are fully considered. Some possibilities suggest that the collapse stops before reaching infinite density, forming an extremely dense core instead. Others suggest that information is somehow preserved, encoded on the boundary, or redistributed in ways we do not yet understand. There are even ideas that suggest black holes may connect to other regions of spacetime, though these remain speculative. For now, the singularity remains undefined, not because it does not exist, but because we do not yet have the tools to describe it. And so, As we move closer, we are not just approaching an object. We are approaching a question about the nature of reality itself. What happens when gravity becomes absolute? What happens when time and space lose their separate meanings? What happens when the laws we rely on can no longer fully explain what we observe? These are not questions with simple answers, but they are questions that objects like this black hole force us to confront. Because at this scale, at this depth, the universe is no longer just a place we observe. It becomes something we are still trying to understand. And as we are carried forward with no path but deeper, we move toward that final boundary, not of space, not of time, but of knowledge itself. And now we are very close, closer than any observer has ever been, closer than any signal could ever describe. The journey has been long, slow, almost peaceful at times. But here, in these final moments, everything begins to converge. The stretching, which once felt gradual, now becomes overwhelming. The difference in gravity between even the smallest distances grows so extreme that structure itself begins to lose meaning. What was once a body, then a collection of molecules, then atoms, is now being drawn into something thinner, more extended, and more fragmented. Not violently, not suddenly, but with absolute certainty. This is the final expression of tidal forces, where the geometry of spacetime no longer allows objects to remain intact. Every bond, every force that once held matter together, is now competing against gravity that changes too rapidly across space. And gravity is winning. Yet even here, something remarkable remains. The experience from within still feels continuous. There is no abrupt ending, no clear moment where everything stops. Just a steady progression, deeper, further towards something we cannot see, but cannot avoid. Because the singularity is no longer ahead in the way we once imagined. It is now imminent, not a distant point in space, but the next moment in time. And this changes how we must think about what comes next. In our everyday world, we imagine endings as locations. You arrive somewhere, and something happens. But here, the end is not a place you reach. It is a moment you become part of. And as we approach that moment, our ability to describe what is happening begins to dissolve. Because all of our language, all of our concepts, are built on experiences that no longer apply here. Distance no longer behaves normally. Time is no longer something that flows uniformly. Cause and effect begin to blur. We are entering a regime where our current understanding of physics, both classical and quantum, cannot fully describe what is happening. General relativity predicts a singularity, a point of infinite density, where space-time curvature becomes infinite. But as we have already felt, infinities are not physical experiences. They are signs, signals that our equations have reached their limits. And so, something else must be happening here. Something beyond what we can currently calculate. Some theories suggest that instead of collapsing into an infinitely small point, a matter may reach an extreme but finite state, where quantum effects counteract further compression. Others suggest that the very concept of space and time breaks down, replaced by something more fundamental. There are ideas that information, everything that has fallen into the black hole, is not destroyed, but transformed, encoded in ways that are still hidden from us. And this brings us back to one of the deepest mysteries we encountered earlier. The question of information. If everything that falls into a black hole simply disappears, then information about its state, its structure, its history would be lost forever. But the laws of quantum physics suggest that this cannot happen. Information must be preserved, and yet, from the outside, it seems to vanish. This contradiction, known as the information paradox, remains unresolved. And here, at the threshold of the singularity, we are standing at the heart of that paradox. Because whatever happens next must somehow reconcile these two truths, that information cannot be destroyed and that nothing escapes. Perhaps the answer lies in ways we cannot yet observe. Perhaps it is encoded at the boundary, subtly preserved in the radiation that black holes emit over vast stretches of time. Or perhaps the structure of reality itself is more complex than we currently understand, allowing information to persist in forms we have not yet discovered. For now, we do not know, and that uncertainty is not a weakness. It is an invitation, because black holes are not just objects to be studied. They are gateways to deeper understanding, places where our theories are tested, stretched, and ultimately refined. And this black hole, this immense ancient structure, is one of the most powerful examples we have. It forces us to ask questions we cannot yet answer. It reveals limits we did not know existed, and it reminds us that the universe is still far more mysterious than we often assume. As we move into this final moment, as everything we are becomes part of this deeper structure, there is no dramatic conclusion, no final flash, no clear boundary, just a quiet transition into something beyond description. And in that silence, there is a strange kind of clarity, because even though we cannot see what lies beyond, we understand something important, that the universe is not finished, that our understanding is still growing, and that somewhere beyond this point, the answers may already exist, waiting. If you are still here, still listening as we reach the deepest part of this journey, gently leave a 2 in the comments. And when you're ready, we will step back from the darkness and begin to understand how something like this could ever have formed at all. Now we step back, away from the darkness, away from the singularity, away from the edge where space and time lose their meaning. And as we return to a safer distance, a different kind of mystery begins to take shape. Because everything we have just experienced, everything this black hole is, leads to one unavoidable question. How did it form? Not just in general, but how did this black hole become so massive so early in a universe that had barely begun? To understand why this is such a problem, we need to gently rewind time, not by traveling through space, but by following the history of the universe itself. The light from this black hole began its journey more than 10 billion years ago. That means we are seeing it as it existed when the universe was only about 3 billion years old. Just 3 billion. That may sound like a long time, but in cosmic terms, it is still early. Galaxies were still forming. Stars were still being born in vast numbers. The universe was more chaotic, more crowded, more full of raw material than it is today. And yet, even in that young universe, this black hole had already reached tens of billions of times the mass of our Sun. That is the mystery, because according to our current understanding, black holes are not born that large. They begin small. When massive stars reach the end of their lives, they collapse under their own gravity, forming black holes that are perhaps a few times, or maybe tens of times, the mass of the Sun. These are called stellar mass black holes. From there, they can grow. They pull in gas. They merge with other black holes. They slowly gain mass over time. But there is a limit to how fast this growth can happen. And that limit comes from light itself. As matter falls toward a black hole, it heats up, just like we saw earlier. That hot material emits radiation, and that radiation pushes outward. It creates pressure that opposes the inward pull of gravity. If too much matter tries to fall in too quickly, the radiation becomes so intense that it pushes the surrounding gas away, effectively slowing down the growth. This balance defines what is known as the Eddington limit. It is not a strict cap, but it sets a natural pace. A black hole can grow, but not infinitely fast. And when we apply this limit to the early universe, something becomes clear. Even if a black hole started forming very early, even if it consumed matter continuously at this maximum rate, there should not have been enough time to reach tens of billions of solar masses in just 3 billion years. The math almost works, but only under perfect conditions. Conditions where the black hole never stops feeding, where it always has access to enough gas, where nothing interrupts its growth. And that is unlikely, because the universe is not that simple. Galaxies evolve. Gas is consumed by star formation. Explosions from supernovae push material away. Black holes themselves, through their radiation, can disrupt the very supply they depend on. Growth is not steady. It is messy, interrupted, chaotic, and yet this black hole exists, which means something must have accelerated its growth. Something beyond the simplest model. One possibility is that it did not start small. Instead of forming from a collapsing star, it may have formed directly from a massive cloud of gas in the early universe. In those early times, conditions were different. The first generations of gas clouds contained almost no heavy elements. Without those elements to help the gas cool and fragment, it may have been possible for entire regions to collapse directly into black holes, bypassing the star phase entirely. These are called direct collapse black holes, and they could begin their lives already thousands, or even hundreds of thousands of times the mass of the Sun. A head start, a way to grow faster, because they begin larger. Another possibility is that this black hole experienced periods of unusually rapid feeding. faster than what the Eddington limit would normally allow. Under certain conditions, if the inflowing material forms a thick envelope around the black hole, radiation can become trapped inside, unable to escape easily. This reduces the outward pressure, allowing more matter to fall in. For short periods, growth could accelerate dramatically. And then there are mergers. In the early universe, galaxies were closer together. Collisions were more common. When galaxies merge, their central black holes can eventually merge as well. Each merger instantly increasing the mass. If this black hole experienced multiple mergers early in its history, it could have grown much faster than through accretion alone. So the answer may not be a single explanation. It may be a combination, a massive initial seed, periods of rapid growth, and multiple mergers along the way, all working together in just the right conditions. But even with these ideas, there is still uncertainty, because objects like this sit at the edge of what our models predict. They are rare, extreme, and they remind us that the universe does not always follow the simplest path. Sometimes, it finds a way to build something far more extraordinary than we expected. And this black hole is one of those creations. But even if we accept these possibilities, massive seeds, rapid feeding, repeated mergers, there is still another layer to this mystery. Because this black hole did not grow in isolation. It grew within a galaxy, and that galaxy was evolving at the same time. In the early universe, galaxies were very different from what we see today. They were not the calm, structured systems we observe in the present. They were dense, chaotic, filled with vast reservoirs of gas that had not yet been locked into stars. This gas was the key. It was the fuel that allowed both stars and black holes to grow. But here is where things become deeply connected. The growth of the black hole and the growth of its host galaxy are not separate processes. They are linked. As gas flows toward the center of a galaxy, some of it forms stars, but some of it continues inward, feeding the central black hole. The more gas there is, the faster both processes can occur. So in a young, gas-rich galaxy, both star formation and black hole growth can happen at extraordinary rates. And this is exactly what we believe was happening here. The galaxy hosting this black hole was likely undergoing an intense phase of star formation, sometimes called a starburst. Stars were forming hundreds, even thousands of times faster than in a galaxy like the Milky Way today. At the same time, gas was being funneled toward the center, feeding the black hole. But this creates a delicate balance, because the black hole does not just consume, it also influences. As matter falls into the black hole and releases energy, that energy does not stay confined to the disk. It radiates outward, affecting everything around it. This is known as feedback, and it changes everything. The radiation from a quasar is not gentle. It includes intense ultraviolet light, powerful X-rays, and streams of energetic particles. This radiation heats the surrounding gas, raising its temperature to millions of degrees. And when gas becomes that hot, it behaves differently. It expands. It resists collapse. It becomes much harder for gravity to pull it inward, either to form new stars or to feed the black hole further. In some cases, the energy output is so strong that it can drive powerful winds, pushing gas outward at thousands of kilometers per second. Entire regions of the galaxy can be cleared of the very material needed for growth. So here is the paradox. The black hole needs gas to grow, but as it grows, it begins to destroy its own fuel supply. It feeds, and in doing so, it eventually starves itself. This self-regulating process is one of the most important ideas in modern astrophysics. It explains why galaxies do not grow indefinitely, why the most massive galaxies eventually stop forming new stars, why the universe, over time, becomes quieter, less active, more stable. And in the case of this black hole, it suggests something important, that what we are witnessing, this brilliant quasar, is not a permanent state. It is a phase, a brief, intense period in the life of a galaxy when conditions are just right for rapid growth. But that phase cannot last forever. Eventually, the gas runs out, or is pushed away, or becomes too hot to collapse. And when that happens, the quasar fades, the accretion disk dims, the black hole remains, but it becomes quiet, dormant, still massive, still influential, but no longer shining across the universe. And this brings us to another quiet realization. When we observe this black hole, we are not seeing its entire life. We are seeing a moment, a snapshot, a brief window during its most active phase, captured by light that has traveled for billions of years to reach us. If we could see it today, as it exists now, it would likely look very different. The brilliant quasar would be gone. The surrounding galaxy would have aged, its star formation slowed, its gas largely consumed or expelled. The black hole would still be there, at the center, enormous and silent, a relic of a more violent past. And this idea that what we see in the universe is not what is happening now, but what happened long ago, is one of the most profound aspects of astronomy. Every distant object is a message from the past. Every photon a record of history. And in this case, the message tells us that the early universe was far more active, far more extreme, than the one we inhabit today. There was a time when black holes like this were more common, when quasars filled the cosmos, shining brightly across vast distances. But that time has passed. The universe has aged. It has expanded. It has cooled. And most of these once brilliant giants have gone quiet, leaving behind only their mass and the subtle influence they still exert on the galaxies around them. And yet, even in their silence, they continue to shape the universe, because gravity does not fade. It remains steady, patient, guiding the motion of stars, the structure of galaxies, the evolution of everything around them. And so this black hole, even after its brightest days are over, will remain at the center of its galaxy, a hidden giant, a silent architect, a reminder of a time when the universe burned far brighter than it does today. As we begin to understand how this black hole may have formed, another question naturally follows. Is there a limit? Is there a maximum size that a black hole can reach? Or could something even larger exist, waiting somewhere beyond what we have already discovered? At first, it might seem like there should be no limit at all. After all, a black hole grows simply by gaining mass. Add more material, and it becomes larger. Merge it with another black hole, and it increases again. In principle, this process could continue indefinitely. But in reality, the universe places constraints, not hard boundaries, but pressures, balances, and feedback mechanisms that make extreme growth increasingly difficult. We have already seen one of these limits, the Eddington limit. As a black hole feeds, the radiation it produces pushes outward against incoming matter. The more massive the black hole becomes, the more energy it releases when it feeds, and the stronger that outward pressure becomes. This creates a natural tension. More mass allows more feeding, but more feeding creates more resistance. At some point, the system begins to regulate itself. Growth slows, not because it cannot continue, but because it becomes harder to sustain. But that is only one factor. There is also the question of supply. To grow into something as massive as this black hole, tens of billions of times the mass of the sun, it must consume an enormous amount of material. Not just a few stars, not even just a small fraction of a galaxy, but a significant portion of the gas available in its entire environment. And that gas is not infinite. Over time, it is used up, converted into stars, blown away by supernova explosions, heated by radiation until it can no longer collapse inward, or expelled entirely by the very quasar the black hole creates. This means that even if a black hole has the ability to grow, it may simply run out of fuel. And then, there is time itself. The universe is not static. It is expanding. Galaxies are moving farther apart. Collisions, which were once common in the early universe, are becoming increasingly rare. And those collisions, those mergers, were one of the fastest ways for black holes to gain mass. Without them, growth slows even further. So while it is theoretically possible for black holes to become extremely large, in practice, the conditions required become harder and harder to maintain. And this leads to an interesting conclusion. There may be a practical upper limit, not a fixed number, but a range. Some theoretical models suggest that black holes may struggle to grow beyond about 100 billion solar masses. Beyond that point, feedback becomes so strong, and fuel so scarce, that further growth becomes extremely unlikely. And this black hole, the one we have been exploring, is already approaching that range. It is not just large. It is near the edge of what the universe seems able to produce, which makes it even more remarkable, because it suggests that we are not just observing a random example. We are observing something close to a maximum, a natural extreme. But even here, uncertainty remains, because the universe has a way of surprising us. Every time we think we understand its limits, it reveals something new, something unexpected, something that forces us to rethink what we believed was possible. There may be black holes even larger than this, hidden in distant regions, or existing at times we have not yet observed. Or perhaps, this truly is close to the upper boundary, a rare outcome, formed under just the right conditions, unlikely to be repeated often. And that brings us back to something deeper, because this question about limits is not just about black holes. It is about structure, about how the universe builds, organizes, and evolves its most massive objects. From stars to galaxies to clusters of galaxies, there are patterns, relationships, scaling laws that connect the small to the large. And black holes sit at the center of that story, literally and figuratively. We now know that nearly every large galaxy contains a central black hole. And more than that, the mass of that black hole is closely related to the properties of the galaxy itself. The mass of the stars, the motion of those stars, the overall structure. It is as if the galaxy and the black hole grow together, influencing each other, balancing each other, evolving as a single system. And in that sense, this black hole is not just an isolated object. It is part of a much larger narrative, a story about how the universe organizes matter, how it transforms simple beginnings into complex structures, and how those structures, in turn, shape the future of everything around them. Because when we look at something like this, we are not just seeing an object. We are seeing the result of billions of years of evolution, of countless interactions, mergers, flows of gas, bursts of star formation, and cycles of growth and feedback, all converging into one enormous presence. And yet, even with all of that understanding, there is still something quietly humbling about it. Because for all our theories, all our models, all our observations, we are still learning, still refining, still discovering. And this black hole, this vast, ancient giant, remains one of the clearest reminders that the universe is still far from fully understood. As we begin to step even further back, away from the black hole itself, something else begins to come into focus. Not the object, but its role. Because this black hole, as enormous and mysterious as it is not just an isolated phenomenon. It is part of a much larger system, a system that spans galaxies, clusters, and the entire structure of the universe. To understand that, we need to look not at the black hole alone, but at the light it sends across space. Because that light has been traveling for billions of years. And along the way, it has passed through countless regions of space, each one leaving a subtle imprint. As the light moves through clouds of gas, some wavelengths are absorbed. Specific elements, hydrogen, helium, carbon, each leave their own signature, tiny gaps in the spectrum where light has been removed. By studying these patterns, astronomers can reconstruct what the light passed through. Not directly, but indirectly, like reading shadows to understand what blocked the sun. And what they have found is extraordinary. Between us and this black hole, there are layers upon layers of structure, clouds of gas stretched across millions of light years, filaments connecting galaxies into vast networks, voids, regions almost completely empty. This is the cosmic web, the large-scale structure of the universe, shaped by gravity over billions of years, where matter flows along invisible pathways formed by dark matter. And this black hole, this quasar, is like a beacon shining through that web. Its light allows us to see what would otherwise remain invisible, to map the distribution of matter, to understand how gas is arranged, how it moves, how it evolves. In this way, the black hole becomes more than an object. It becomes a tool, a probe, a way of studying the universe itself. And this leads to something quietly profound, because without objects like this, we would know far less about the early universe. We would not be able to trace the distribution of gas across cosmic distances. We would not be able to measure how the universe evolved over time. We would not be able to test our theories against real observations. This single point of light carries information across billions of years, not just about itself, but about everything it has encountered along the way. And that information is incredibly detailed. Tells us about temperature, about density, about chemical composition, about motion, all encoded in subtle variations in the light. And this is why quasars are so important, not just because they are bright, but because they are distant. They allow us to look back in time and to study conditions that no longer exist in the present universe. A universe that was denser, hotter, more dynamic. A universe where galaxies were still forming, where black holes were still growing, where the structure we see today was still taking shape. And this black hole is one of the brightest of them all, which makes it one of the most valuable, because the brighter the source, the more information its light can carry, the more precisely we can measure what lies between. But even beyond its role as a probe, this black hole also tells us something deeper about the nature of the universe. It tells us that extreme objects, rare objects, can still have enormous influence. That even a single black hole, in the right conditions, can shape an entire galaxy, affect the flow of gas, regulate star formation, and leave lasting imprints on its environment. And when we scale that idea up, we begin to see a pattern. From the smallest particles to the largest structures, the universe is interconnected. Changes in one place can ripple outward, influencing regions far beyond their origin. And black holes, especially ones like this, are among the most powerful sources of those changes. Not because they are everywhere, but because where they exist, they matter, they shape, they regulate, they transform. And yet, despite all of this influence, they remain hidden, invisible, defined not by what they emit, but by what they take away, which makes them, in a sense, the quiet architects of the universe, shaping structure without being seen, guiding evolution without announcing themselves. And this brings us to a final realization before we reach the end of our journey, that this black hole, as vast and powerful as it is not the center of the universe. It is not unique in its existence. It is part of a pattern, a system, a story that extends far beyond any single object. And yet, by studying it, by following its light, by tracing its history, we begin to understand that story more clearly. Not completely, not perfectly, but enough to see that the universe, even in its most extreme forms, follows patterns we can begin to uncover, and that even in the deepest darkness, there is still something to learn. And now, as our journey slowly comes to an end, we drift gently away from the intensity, from the brightness, from the overwhelming gravity of this black hole, and allow the universe to settle once more into quiet. The light fades, the motion softens, and what remains is perspective. Because what we have witnessed is not just a single object, not just a distant quasar shining across billions of light years, but a glimpse into how the universe builds, evolves, and reveals itself over time. This black hole, so vast that it challenges our understanding, began as something far smaller. It grew, fed by its surroundings, shaped by its galaxy, influenced by forces both violent and subtle. It reached a scale that feels almost impossible. And yet, it exists, and that existence tells us something important. That the universe is capable of creating structures far beyond what we once imagined. That under the right conditions, given enough time, and enough energy, complexity emerges. Not randomly, but through patterns, through interactions, through processes that unfold slowly, patiently, across cosmic time. And yet, even with all of this growth, all of this power, there is still a kind of silence at the center of it, because the black hole itself remains unseen. Everything we have observed, every detail, every insight comes from what surrounds it. The light of the accretion disk, the motion of nearby matter, the imprint it leaves on its environment. But the black hole remains hidden, a reminder that some parts of the universe are not meant to be directly observed, but understood through their influence. And perhaps that is part of what makes them so compelling, because they invite us to look deeper, to question, to explore, not just what we can see, but what we can infer, what we can imagine, what we can slowly uncover through careful thought and observation. And in doing so, they lead us towards something greater, a deeper understanding not just of black holes, but of reality itself. Because in the end, this journey was never only about one object. It was about the limits of knowledge, about what happens when our theories are pushed to their extremes, about how the universe continues to surprise us even after centuries of study. And as we gently return to the wider cosmos, leaving this ancient giant behind, we carry something with us, a quiet awareness that there is still so much we do not know, so many questions still open, so many mysteries still waiting. And that is not something to fear, it is something to appreciate, because it means the universe is still alive with discovery, still unfolding, still offering new insights to those who are willing to look and to wonder. Now, imagine this black hole as it exists today, no longer blazing as a quasar, no longer flooding space with radiation, but quiet, dark, resting at the center of its galaxy, surrounded by ancient stars, its most active days long behind it, a relic of a younger universe, a silent witness to billions of years of cosmic history. And yet, even in that silence, its gravity remains, its influence continues, guiding stars in their slow orbits, shaping the structure of its galaxy, holding together something vast and beautiful. And perhaps that is the final lesson, that even the most extreme objects in the universe are part of a larger balance, a system where creation and destruction, growth and stillness, light and darkness, all exist together, not in conflict, but in harmony. So as you rest, as your thoughts begin to slow, imagine that distant galaxy, far beyond anything we can see with the naked eye. At its center, a black hole of unimaginable scale, silent, patient, endless, and around it, stars moving gently through the darkness, tracing paths that will continue for billions of years. A quiet motion in a quiet universe. And somewhere far away, you are here, listening, drifting, a small part of something vast. If you are still here, still listening at the end of this journey, gently leave a 3 in the comments. And as the universe continues its slow, endless expansion, you can simply rest and let the stars fade into silence.